Black holes. To understand the idea of a black hole, we need to look at basically what is a black hole, what makes it black. The reason it is black is because there is no light that escapes from it. And we get onto the concept of escape velocity. And first of all, we need to calculate escape velocity, derive this escape velocity equation to be able to do the maths to do with the black hole. So describe black holes. We need to basically first of all understand the idea of the escape speed. Now the escape speed or escape velocity is a speed an object must have to overcome the effect of gravity so that it is able to travel to infinity, and when it gets to infinity the velocity will be 0. So the kinetic energy that it has when it leaves the surface of a planet is just enough to overcome the negative potential energy. So you need to look at the equation for kinetic energy, potential energy, and you basically equate them, the changing potential energy, the changing kinetic energy, and you will get a value for V. This is a derivation that you need to be able to do. So we have the kinetic energy on the left is equal to the negative potential on the right, and you will basically find out a value for V. And what you find V squared is equal to 2gm over r. Now we're looking at a black hole, so this velocity that we're talking about, this escape velocity, is actually going to be the speed of light. It's light that is not able to escape from a black hole, from what we must define as the surface of the black hole. If we make V equal to this speed of light, and r is going to be the radius effectively of the black hole, or basically the distance from beyond which light is not able to escape. So we basically want to focus on what r is, so we just rearrange that, and we have r is the radius of the black hole. It's not the radius of the material that's in a black hole, it's basically what we see as being the event horizon. It's the point beyond which we're not able to see the light from inside because it's not able to escape. You remember that near a massive object the four-dimensional space-time is going to be curved close to the object. The closer you get to the object, the steeper the curvature. So light is going from the left to the right here, and it follows this short path here, so it's going to be following this geodesic, this the straightest line that it may in this trajectory. And this is a star. That the escape speed is basically limited by the size of the star. Now let's say this star is to be reduced to a point, to a singular point, a singularity. In other words, it becomes a black hole. At some point this curvature is going to be so steep that light is not able to escape. And this is what we have here. The star, this is a star before collapsing. After it collapses, it makes the curvature so rapid here, such steep curvature, that there will be a defined ring here, which will be the event horizon. The curvature here is so steep that light is not able to escape. This is called the event horizon. So when matter from the star is reduced to a singularity, to a point, beyond this red line, the curvature of space-time is so great that not even light can escape. And this is when we have a black hole. You know that the escape velocity, the kinetic energy and the potential energy have a value which are going to be equal of the change of kinetic energy and the change of potential energy. So we substitute for C for V, we swap round and we get a value for R. R is called the Schwarzschild radius. And here we have it. RS, Schwarzschild radius, is equal to 2gm over c squared. You need to know what g, m and c and rs are. So c is the speed of light, m is going to be the mass of the material in the black hole, and r is not the surface of where the material reaches, it's the point where the event horizon is. So the Schwarzschild radius is the radius of the black hole from within which nothing, including light, can escape. It was also called the event horizon, and it's not the physical surface of the black hole. Schwarzschild radius, according to previous Mark scheme, is the radius from within which nothing can escape to the outside, not even light. Or it's the event horizon, the distance from the black hole where the escape speed is equal to the speed of light. You can define it that way, because remember, the black hole is a singularity, is a point. So it's a distance from the black hole. It's not the surface of the black hole. From within this surface, mass has disappeared from the universe. The center is a single point or singularity to which all mass would collapse. Now we need to calculate the Schwarzschild radius given values. If we have for Earth, the mass of the Earth is 6 times 10 to the 24. G is equal to 6.67 times 10 to the minus 11. If the Earth were a black hole, if all this mass were a black hole, how big would it need to be? What would be the size of the Schwarzschild radius? So, if the Earth were a black hole, where would the escape velocity be? What would the radius be? And you should try to work that out now, and you will find a value which is something like 2 or 3 centimeters. The Earth would need to be, the Earth in terms of the Schwarzschild radius would be the size of a ping pong ball. You know that low clocks go slow, high clocks go faster. Now, how is this going to work with a black hole? It means that the closer you are to the black hole, the slower your clock is going to go. Or rather, the closer you are to the event horizon. When you reach the event horizon, then the clock is going to be going so slowly it will stop. And this is a really strange thing, because when we think about objects falling into black holes, as we observe something falling into a black hole, as it falls in, its time will go slower and slower and slower. So we are never going to be around long enough to see anything actually cross the event horizon, because the time it would take would be infinitely long. So we need to solve problems involving the time dilation close to a black hole, and this is the equation that we use. So delta t is a time interval very far from the black hole, so we're observing the black hole from a long distance. This is the time interval which is near to the black hole. S is the Schwarzschild radius, and then R is the distance from the black hole, or from the solar singularity, that this object is, this thing that is close to the black hole, the one that has delta t naught. R will be the distance that it is from the black hole. We are at a distance which is infinity. So solve problems using the gravitational time dilation formula. A space probe we send off approaches a black hole. It sends signals to a faraway observer, which is us. When the distance from the black hole is 1.5 times the Schwarzschild radius, the probe stops and sends 2 signals which are 1 second apart. How far apart are signals to the observer? So you try to do this now. Some help. Delta t naught here is going to be 1 second, because that as far as the transmitter is concerned, this is the time interval close to the black hole. R is the distance that this object is from the black hole, which we know is 1.50. That's Schwarzschild radius is, the radii. You know RS is just going to be RS, and you'll find that the delta t will be increased. So an event which takes 1 second close to the black hole is going to take more time here. So you can just calculate that. You'll find a value of 1.73 seconds. The next question is, what if the pulse is transmitted at 1000 Hertz? What is the observed frequency? I put this equation here, but this is not one that you may use. This is about gravitational redshift, which is basically what we're looking at. However, this is only to do with small changes in the gravitational field, where delta H, the field strength, is going to be constant over that distance. So you mustn't use this equation. This is to do in a gravitational field like on the Earth, and it's going to be a very, very tiny amount. This is going to be much bigger. So we need to remove that. How do we do this? Well, we know we have 1,000 Hertz. We change this 1,000 Hertz to what is the time interval between each wave. And we do the same thing here. We have to work out what is the time interval here when that's 1,000 Hertz, and then find out what the time interval is here, and then convert that back into frequency. What you find is that the interval of 1 second from a far distance will be seen as 1.73 seconds, and the frequency which is emitted, which is 1,000 Hertz, by the time it gets to us, will be 578 Hertz. In other words, it becomes very much redshifted.